All right, so neuron communication is electrochemical, and you probably recognize that the two parts of that word are electricity and chemical, and that really is the two parts of the communication. That part of the communication that we've touched on a little bit already in that last video is chemical, and the chemical refers to that neurotransmitter and how it's used. Um, but then the electrical part is what's happening within the neuron. So in order to get the message from the dendrites to the axon, that is an electrical process. And sometimes students think that I'm talking figuratively instead of literally when I'm talking about the electrical process. But as you'll see, we are being quite literal. Our bodies are electrical machines, and you may or may not ever have stopped to think about that. But we measure, even in terms of some medical tests, we measure how your electricity is working. So some of you or family members may have certainly had an EKG, an electrocardiogram, and they put electrodes on your body to see how those electrical messages are working in your cardiovascular system. And abnormalities mean that they see something atypical in how the electrical messages are being sent and what the rhythm of those messages are. Similarly, you may know somebody who has had an EEG or an electroencephalogram, and that's when they put electrodes on your head to measure how electricity or electrical messages are being sent in your brain. So it's, so if you haven't paused to think about that, I want you to think about the fact that you're testing your electricity with those tests. I assume most of you know that you don't want to add electricity to your body. That's called electrocution. And essentially it overloads our electrical messages, our electrical circuits. And that, is a very bad thing. So very literally electrical within the neuron. And so we talked about this a little bit. I'm just looking to make sure, I just want to re-emphasize that in the chemical communication is about that neurotransmitter fitting into the receptor site, or when it's being sent, the neurotransmitter being sent out into the synapse to find a receptor site on the next neuron. And I mentioned before in the last video that the receptor sites have a specific shape, and the molecular structure of a specific neurotransmitter has a unique shape, and that those two shapes need to fit together. We call this the lock and key analogy. That the key is the neurotransmitter molecule, and the receptor site is the lock, and they need to fit together. So most of you understand that if you have traditional keys, they only open one door because the key has a shape that has to complement the lock shape. And so, it has to fit in, and then the teeth on it have to fit into the grooves of the lock. And the same thing has to be true of the neurotransmitter and the receptor site. And again, we're talking in a very literal way here about shape, not speaking figuratively. And this is really important because it means that any given neuron is not going to get an incorrect message by having the wrong neurotransmitter tell it that it should fire. It has to be the right neurotransmitter to fit and make it fire. If the wrong neurotransmitter that doesn't the right shape tries to enter the receptor site, the neuron won't turn on. There is an interesting exception to this that kind of proves why it's so important. And the exception is that opiates, things like heroin and Oxycontin, have the same molecular structure as a set of neurotransmitters called endorphins. And endorphins are kind of our feel-good neurotransmitters. And heroin and similar substances have the same molecular shape, and our neurons can't tell the difference. And so they turn those neurons on. They tell them to send a message, even though they're not actually endorphins. What happens, though, then, is that your body has extra endorphins that aren't being used because something's already occupying those receptor sites, and it cuts back on the production of endorphins, so that if you try to stop using the opiate, the heroin or whatever it is, you then feel quite sick because you don't have enough endorphins to keep you from feeling sick. It's one of the things endorphins do for us. And so so it's an example of where the rule doesn't work. But it is also an example of why the rule is so important. So Neurotransmitters can either be excitatory or inhibitory. Excitatory is what it sounds like. It excites things, and specifically here, as we talk about neurons, it tells neurons they should fire, that they should send a message. Inhibitory neurotransmitters tell neurons that they should not send a message. And that sounds odd at first, but there are lots of times when we don't want action to happen. So if I'm going to hold my hand out like this and hold it still, in order to hold it still, I need to be sending messages to stop it from shaking and moving, right? And that would require inhibitory messages. Even when I pause there between my words, that relies on inhibitory messages, and most of us understand that our heart needs to beat, but also needs to pause between beats, and that pause is also about inhibitory messages. So all of these are good examples of why we might want to tell a neuron not to fire. So we start with a neuron at rest, right? And this little image here showing you that when a neuron is at rest, there's a whole bunch of positively charged sodium particles, that's that Na, outside the neuron. And they're being kept outside the neuron because at rest, the neuron is impermeable. And so impermeable is essentially as if you had a saran wrap and moisture couldn't go through it, right? Because it's impermeable. It doesn't let things through. And the cell membrane of the neuron is impermeable when it's at rest. And because it's impermeable, those sodium particles can't get through. We're talking about sodium because these are charged ions. You'll see inside the neuron there's a couple of those K+, it's potassium. There's also chloride molecules that are hanging around and have a role here. You guys I'm saying ions, you could also think of these as electrolytes, and you probably are more familiar with that term because it's marketed in Gatorade, and Gatorade tells us how important it is to replenish our electrolytes, and they're not wrong. I don't know if you need to drink Gatorade to replenish them, but electrolytes are very important. That one of the reasons why we need those electrolytes is to keep our heart going and our cardiovascular system going. But really, in the background of that is that we need to keep our neurological system going so it can keep those other things going. And so at rest, the neuron is not doing anything. It has what we call a negative charge, and that all we mean by that is that the outside fluid has more positive electrolytes and is more positively charged than inside the neuron because of that impermeability. When the first neuron in a sequence sends a message, right, the chemical piece is that it releases neurotransmitter into the synapse, as we see here in this image with these green circles, and then those gold cup-like structures to the right with those arrows pointing at them are the receptor sites that those neurotransmitters are going to fit into. The moment those neurotransmitters enter the receptor site, that neuron says, I have a message. And as long as it's the right neurotransmitter and the right receptor site, and they fit in that lock and key analogy that we just talked about, the neuron says, I have a message. And the moment it says it has a message, we change from this chemical communication that we're seeing in this image to an electrical communication. That at the moment it says I have a message, its cell membrane right there near the receptor sites becomes permeable to those sodium ions or electrolytes that we just talked about. And they come rushing into the neuron. And as those positively charged particles come rushing in, that negative charge that the neuron had becomes positive because of the addition of those positive electrolytes. It immediately then, though, the neuron immediately then pumps out positive ions and both sodium and potassium ions to go back to its negative state. And it quickly, therefore, goes from a negative to a positive to a negative charge. And that switching back and forth in charge is electricity. And if you think about batteries and how carefully you need to look at the positive and negative ends and match them, when you put batteries in, what you're doing is making sure that the positive and negative charges can be exchanged, because that's what makes electricity in very literal ways. And so this is why we're talking about the electrical part of the communication. So it's that change in permeability positive ions come in, we go to a positive charge from our negative resting state, and then back to our negative resting state, and that's the electrical part. Um, but this doesn't happen in the neuron all at once. So I said before, the permeability changes just by the receptor sites, and we have this back and forth in charge right there. And then as the charge goes back to negative, it triggers a change in permeability at the next little bit of the neuron. And just like a wave in a sports stadium, it goes all the way across the neuron till it gets to the terminal knob, the terminal button. And then we get the last sequence of what happens that we'll come to in a second. So we get this wave of back and forth, negative, positive, negative, switching all the way down the neuron. And this is where that myelin comes in, because myelin is an insulating fatty substance. It speeds the process up because it allows the wave to move more quickly down the axon. There's little spaces in between the myelin called nodes of Ranvier. And any axon that has myelin on it, it doesn't have the change in permeability at every spot along the axon, only at those nodes, only where there's a space. And the fatty substance really is like having rubber around a wire. So you're used to seeing wires in your walls or in other places that have rubber around them, and that's to prevent the electricity from coming out along the way, right? And the myelin acts the same exact way. But if you were to cut a little slit in that rubber coating, then electricity might come out through there, and that's what the node of Ranvier does in terms of that change in charge. Once that wave reaches the terminal knobs or the terminal buttons, the change in permeability gets there. And think about this: the change in permeability, right, is about opening hatches, essentially opening little spaces in the membrane. When that happens at the terminal buttons, then neurotransmitter molecules can escape. And then they're released into the synapse, and we start the process all over again with the next neuron. And so the release of neurotransmitter is going back to chemical, right? So we're chemical at the first synapse, the presynaptic, the synapse before the dendrites, and we're chemical again when it's released into the next synapse, and we're electrical in between. So the last thing I want to say here is that we want to go back to that excitatory or inhibitory choice of neurotransmitters. Almost all neurons have receptors that will respond to more than one, have kinds of receptors that are ready to respond to more than one neurotransmitter. So any one receptor site only responds to one neurotransmitter, but a neuron is going to have different kinds of receptor sites. Some of those are going to allow excitatory neurotransmitters in to tell that neuron to turn on, and there'll be other receptor sites that are for inhibitory messages to tell the neuron not to turn on, not to fire. And really, it is just a matter of which one wins. It's just really a matter of how many of the receptor sites do enough of the excitatory ones get filled to reach a threshold that tips it over into firing, or are more of the inhibitory ones turned on. And this is the all or none principle. Like, the neuron either turns on or it doesn't. Everything we just talked about happens, or it doesn't happen at all. There's no weak firing or strong firing. It is one or the other. And then the last thing to make note of is the idea of reuptake. And reuptake, it happens in the synapse before the message is sent. So when we send neurotransmitter into the synapse, right, the terminal button sends neurotransmitter into the synapse, there's almost always more neurotransmitter release than will be taken up by the receptor sites. And if we left that there, we just left those extra molecules hanging around in the synapse, they would just by chance find their way later on to the receptor sites, and then the neuron would think it was supposed to fire again. So you'd raise your hand in class, you'd put your hand down, and a couple of moments later, there would be this accidental message sent, and you'd raise your hand again, even though you had no intention to do so. And so reuptake, there are transporter molecules that attach to the neurotransmitter molecules, and they take them back. And that's where this reuptake channel is that you see, where they get brought back into the sending cell, into the neuron that sent them out to start with. And when we talk about serotonin in the next video, we'll talk about serotonin reuptake inhibitors. And those are medications that stop the reuptake of serotonin, and we'll talk about those when we get there. So I'm going to skip that. We'll talk about them then. All right, so we're going to pause there, and then in the next video, we're going to talk about some examples of specific neurotransmitters.